Good morning. First, I'd like to thank you for the opportunity to speak here today. Second, I thought that last talk title was rather interesting because this was the title which I sent to security, and from high up in the chain, I got a call, and it said something. There's this. Maybe it was leaked. I don't know. Initial experiences accelerators at NRL. And I said, oh, no. This is the title. I'm not submitting it through security again. Otherwise, I probably won't get it there on time. So, another warning. Although my official job title is computer scientist, my boss often introduces me as a mathematician. So, I guess I'm not a very convincing programmer. So first, I'll just talk a little bit about what is an FPGA. Probably some folks have forgotten because, well, they've probably been looking too much at the GPUs. Then I'll talk a little bit about the programming approach, and we'll then look at matrix multiplication. You're probably wondering, well, why matrix multiplication? What's interesting about that? Well, what's interesting is this Convey architecture, which is designed to solve the memory bottleneck. And matrix multiplication has lots of parallel opportunities for computations, but the real limitation is the I/O capabilities of the device. So that's what makes it interesting. OK, so an FPGA, what is an FPGA? A CPU basically has three functions, right? Fetch, decode, execute. It has a brain. And so an FPGA doesn't have a brain, and an FPGA doesn't have a program. So an FPGA is basically a matrix of logic blocks, mainly lookup tables and flip-flops. And so a programmer configures these components in order to perform logical mathematical functions. We can think of such configuration as a known state, so that we can power on the FPGA, and then it will be in exactly that state. So Xilinx has been the vendor for the last 3 decades. There's been more than one vendor for about half of that time. The Virtex, I've been working with the Virtex-6s. Key point to note about them is that they have slices for doing 18 by 25 multiplies. And they have these 48-bit wide 3-input adder, subtractor, accumulator. So just a little bit about the HC1. So HC1 was supposed to be the HC2, which has the Intel Quick Path interconnect, but they didn't get it really out on time. So they settled for the front side bus. What's in the box? So of course there's the quad-core Xeon processor. There's the co-processor, which has the 4 user programmable FPGAs. This initially came with 32 gigabytes of memory. Half was shadow memory for the coprocessor, and half is user memory. And I actually had to double that to 64 because when I was doing just a few builds, very often I would crash the system. So after I doubled the memory, that seemed to solve that problem. So there's also each of these memory banks. There's 8 of them. They're 2 gigabytes each, so that's a total of 16 gigabytes. There's 8 memory channels, memory controllers. Each of the FPGAs has 2. Okay, what else I wanted to say? Okay, so what's cool about this architecture is that the host can communicate with the coprocessor using standard 86 protocols, and the host can write to the FPGA's memory, and the FPGA can access the host memory, and of course it's faster to access local memory. So what else we want to say? The FPGA has 2 ports to each of the 8 memory controllers, so that's 16 ports. The tricky part is if we want to write data to a particular memory bank, then we need to specify the memory channel. The easy part is if we have the address, then we know the memory channel. So that's the easy part. All right, so just quick summary. FPGAs are unlike CPUs, despite the fact that a lot of folks just want to add pragmas and to their Fortran and C code, which is okay, but you don't expect to get the real performance unless you're going to be beaten probably by a GPU. So the programming has to be different. And again, what's cool is the novel memory system, which was designed by Convey. Okay, so a little bit about software development. Again, an FPGA configuration is written in a hardware description language such as VHDL or Verilog. And there are other alternatives. So what I'm using, well, that's what I'm using. Bluespec system Verilog. So the cool thing about my job actually is I not only get to work with this really cool hardware and cool software, I get to actually get sometimes these companies working together, because like Bluespec and Convey, they weren't working together before. And so in order for me to use Convey's system, you have to understand too that there's a lot inside the box, right? So there's those 4 FPGAs which I'm programming, right? But there's a lot of other FPGAs which manage the system, right? Well, I don't have to program those, luckily. Convey has a layer there which I don't want to particularly myself deal with too much. So I want to use the Bluespec. So some libraries had to be developed. So that was the collaboration between Convey and Bluespec. They built those libraries so then I could program in the Bluespec system Verilog. So the key point, though, is if you want to design a circuit, okay, suitable for an FPGA, you can't do it in these other like C-like languages, Impulse C, Mitrion C, and that kind of thing. And you can't do it with pragmas. So Bluespec system Verilog is a really good alternative to VHDL or Verilog. So why choose Bluespec system Verilog? Previously, I actually programmed in Mitrion C, and again, I couldn't you could do a lot of amazing and fun things with Metron C, but you could never design a circuit. So you can do that with Bluespec System Verilog. And yet the language is still a high-level language. So I don't have to manage a lot of minute details that you would have to do if you were doing just like VHDL. And furthermore, their approach is based on atomic rules, which allows you to it enhances software development. And you're able to avoid a lot of programming errors that you typically would run into if you were using just a very low-level language like VHDL. Can everybody hear me? OK, so as an added perk, they have their simulator runs real fast if you compare to, for example, using Convey's, if you just use Convey's software. OK, so I don't work for Bluespec, by the way. So just want to make that clear. So just remember what is matrix multiplication. So basically, your input is two matrices, say A and B, and the result is a matrix, say C. Each cell in C is a result of multiplying two equal length vectors and produces a single number. So that basically you multiply a number in any row at some offset by the same offset, the number in the column there, and then you add them all up and you get the result. So again, there's a lot of all these multiplies can be done in parallel, so lots of opportunities for parallelism, but we obviously can't do everything at once. First of all, we can't read everything at once, and second of all, we can't write everything at once. So there's some obvious limitations. So the very natural thing to do is, instead of computing a cell at a time or iterating over rows and columns, what we're going to do is the usual block matrix multiplication. So this view is the low-level view of how we're going to do the computations on the FPGA. Depends on the block size used, of course, and which in turn depends on what will fit on the FPGA. So this is the low-level view. The top-level view is just a larger block matrix multiplication algorithm. So basically, and there's not only one way of doing it, but this is the way I'm doing it. So just divide A into 4 large blocks, and then assign each one of them to one of the 4 FPGAs, so that each FPGA is going to read the whole B block, but they're only going to read one of those 4 blocks of A, and they're only going to write one of the 4 blocks of C. So the key point, of course, is that we don't have to program the FPGAs differently. We just give them a different starting address and possibly a different size. OK, so initially I worked with 64-bit integers. Why? Well, when you're working with new tools and new hardware, you don't want to work with real numbers. So starting out with, in fact, using another language, for example, if you have something wrong with the code, it's very hard to figure out what's wrong with it if you don't know the numbers. So although I was doing this with 64-bit numbers, had lots of successful simulations, synthesis would always fail. And what is synthesis? Synthesis is the chip maker's way of mapping your codes to configure the device so you can actually run it. And what was the reason for the failure? Well, the 64-bit multiplies. Remember when we talked earlier, I'm using the Virtex-6s, and they have only, what's on there? Remember, they only have this 25 by 18 slices for the multiply. So the Xilinx tool is actually smart enough so that I could say in my BSV language, OK, multiply these 64-bit integers. And that could get written into the Verilog, and then the synthesis tool was smart enough to figure out, OK, how to break it up. But it wouldn't break it up in a nice enough way that timing would be achieved. So, OK. I was not particularly interested in integers anyway. I wanted to do floating point computations, and I couldn't anymore delay doing that. So now I have two problems. I have to develop the code I have to implement this 32-bit single precision numbers. The problem is there is no runtime support for floating point numbers. So I have to write all of that code. And starting with the IEEE standard representation and doing all the coding and testing, and then of course the second problem is I have to do that in a way so that I break up the operations so that I'll achieve the timing. So I won't run into the same timing problems. OK, so here's just a oops. Here's the Bluespec code to show my own internal representation. So you can see that I basically used 48-bit significant. I wanted to do that, like basically near double precision calculations. And so this is the key thing about FPGAs, is that we can not only accelerate the application, but we can do it more accurate. And this is important because, especially with like doing these kinds of scientific computations, round-off error is a big problem. But I don't want to talk about round-off error because I have enough. I don't want to spoil my reputation any more than it already is. So anyway, moving on. So the initial parallelization technique was that you always, whenever you're doing a parallel mapping something to some kind of device, you always want to be keenly aware of the architecture, right? And you have to get it right. Well, we have these 8 memory banks, and let's see. Well, an inner product is associative and commutative, even though matrix multiplication isn't commutative. So it's very natural to think that we could kind of think of this long, big inner product and just take chunks of it and do it and then add it all up together, basically, right? So basically, we could associate with each memory bank and each memory controller, we could associate, let's say, a CPU process that does all the segments that lie in its memory bank, right? And then add them all up at the end. The only problem is we're not actually, there is no CPU process, right? It's a configuration. And so, OK. This, by the way, this was how we actually did the vector add example, which Convey did. This was done this way. So it was sort of a natural way to think of doing it on the with matrix multiplication. So this was a very complex code. I did a lot of work to reduce the complexity, but finally, I did a lot of statistical analysis, but again, I don't want to talk too much about that. In the final analysis, however, I realized this was never going to work. So this was just an inherently bad design. seemed like a natural fit, but it just, we would never get an optimal solution with this design, so had to start over. So some of the optimizations I did was to, so initial work was, we had all these kind of alignment assumptions, and I just had to throw that all out the window. Forget about alignment. And then another thing which we learned, actually this was kind of a cool thing, because when Bluespec first did their version of Convey's vector add, it wasn't running quite as fast as I wanted it to run. And I kept pressing them, well, why is it? And this guy from Bluespec, he's really a guru, he kept saying, well, in principle, we should be able to get it running just as fast. And I was like, well, why isn't it running as fast? So it's not running as fast. And well, we finally found out, it was kind of proprietary under the hood, how the engineers at Convey, they figured out that there was sort of a magical number that, if you do, you don't want to interleave the reads and writes. You want to do just a magical number of the reads and then the writes, and then you'll get this really good performance. So that was a trick. And once we kind of communicated that, then Bluespec's code was actually faster than Convey's code. So really cool. Sorry, I got distracted. Where was I? OK, so there were a number of optimizations which I wanted to do. But mainly what I did was, and just in a nutshell, was so just forget about all this nice segments and just do the whole bloody thing. Give the whole inner product to a process. God forbid I said that. Again, it's a configuration. So what this is sort of a depiction of my circuit, okay, to use better language. So this is actually, what is this actually? So basically what I'm trying to depict here is MAC, of course, stands for multiply and accumulate. I have two pipelines here. And what I'm doing is, remember, what I've chosen a block size of 8 by 8, mainly from experience. And so what that means is I got 8 rows and 8 columns, right? I'm going to use 8 rows of it. So each FPGA has a block, and we're going to do 8 rows at a time and 8 columns. So these two pipelines, you can think of it as doing a single column. So basically, why are there two pipelines? Well, we want to kind of push things always to the limit. So we're going to do 64-bit reads, even though I'm actually doing 32-bit multiply. So we're getting two words at a time. So that's why we basically have two pipelines. And I'm using time division multiplexing, which basically means each stage is running at every cycle. I'm doing 8 inner products, and what else? So it's very efficient, right? So it's very efficient, and because we're reusing the software, right? So we're reusing the hardware, and so we don't need to have so many kernels. So if you know of some application that you think that would be really suited, I would be very happy to talk with you about it. I know Paul probably wants to ask, what's the good, the bad, and the ugly kind of thing. So maybe the bad and the ugly. I've had some bad experiences with the Virtex-6s, I have to say. It's like a really kind of a whack-a-mole kind of activity where a lot of iterations, it doesn't achieve timing. You have to kind of go through all the reports, you have some big path, make a hypothesis where things went bad, and go all over again. So it can be rather unpleasant. But I've heard some very good things about the Virtex-7s. So I've heard a lot of people say that the Virtex-7s had a very good experience. And another bad thing is I've actually had some, after struggling to get the timing, I've had problems where the codes don't actually run on the hardware. So that was, but these are just normal things, right? You're working with these kind of new technologies. These are normal, and we'll get past them. So that's bad. The good, I would like to just say that I think it's really great what Convey has done, and Bluespec too. I think they're really, really smart people there, and I'm very happy to be working with them. So thank you.